Thanks, everyone. Thanks, Maria. Hi, I'm here to talk to you about a native query planner in Apollo Router. As we say, on the other side of the ocean, which is where I live. I will use router interchangeably because that's just how it is. Hi, I'm Irina. I'm a senior staff engineer here at Apollo. I work with a lot of compilers. That's been my interest/work over the last 6 years. And it just so happens that I also started doing Rust 6 years ago at one fortunate Rust Fest event in Paris in May. So that's me. And we're going to talk about the Query Planner, which we launched as a public preview in Router 1.56. And specifically, we'll talk a lot about its implementation and how we got to where we got, and what steps we take to actually get to this public preview. It's implemented in Rust. Surprise, a Rust engineer is going to talk to you about Rust. Who would have thought? But before we kind of dig into how this process went, let's talk a little bit about some numbers and what are the things you'll get out of this whole implementation. And these are some of the things you saw yesterday during Matt's keynote. But on a micro level, in terms of query planning itself, we've seen a whole drop in query planning duration in terms of how long it takes to plan a query plan. On average, it's about a 10x improvement in terms of just how long we can plan an operation. This is great for us in terms of something we want to release for public preview. In terms of CPU usage, we've seen a drop as well, and a lot of this can be summarized to something around a 2.2 improvement. Sometimes you should wait, because sometimes it's a 5.5 improvement. Depending on how complex an operation is and how much kind of the underlying libraries have changed, this can be seen as a 5.5, which is really, really great. And we also wanted to look at a macro level of what it looks like for the router in terms of its memory consumption. And so we did some load tests for that as well. And we've seen a pretty significant drop as well. Sometimes around 2.2, sometimes a bit more. And in certain cases, when we looked into kind of using a query planner pool in JavaScript versus using a query planner pool in Rust, yes, and there is math on this, but you can see that the drop is a lot larger. And so this is what's coming, and we're excited about its public preview, but I really want to talk to you about the effort that went into it and what we did under the hood. So the plan for this talk is we'll talk a little bit about the router, or the router. We'll talk about the existing query planner implementation. We'll talk about the whole rewrite process, and we'll talk about what's coming up next. So let's talk about the router. So the whole story starts with Rust. Oh no, the Rust engineer is talking about Rust. So a few years ago, we made a decision that Rust is our path forward at Apollo to really build a stable, reliable, and high-throughput software that we like our users and customers to use. And over the last 4 years, we've been slowly transitioning various parts of this critical infrastructure to really be the backbone that is stable and reliable. And we started and kind of progressed over the years. So the one thing you already know that works in Rust is the router. This is a highly simplified version of this diagram because there's no more space if we fit everything in. So just kind of like as a simple thing, this is what routes and executes the requests coming in. We started rewriting this about 3 years ago. Parts of this are handled by Apollo REST, and that's our GraphQL tooling to parse, validate, and compile GraphQL to Rust. This is nested inside the router and is also now used for the language server that Trevor was talking about yesterday. A huge backbone for really a lot of the GraphQL things we want to do in Rust. Rover, which is a tool, the CLI we use to talk to GraphOS, but in the context of this, it's something that actually composes the supergraph schema and feeds it into the router. But there is one thing that remained, and it's missing from this diagram, and that's, you guessed it, surprise, is the query planner. And this is how it fits inside the picture here. The query plan is created based on the supergraph schema. We generate that plan, but that's talked through a separate sidecar system. And this is the one that we actually ended up rewriting here. So, what's the query planner? Well, the query planner is something that breaks down an operation that comes in and creates most optimal paths for you to be able to get the data you need from the subgraphs or REST endpoints. Sometimes it's quite simple. There is various 3, 4, 5, 6 subgraphs that various pieces of data come together. A lot of the times, it's a lot more complicated. And this is like a below average level of complicated. The average level of complicated will not fit in the slide. I think it's missing something here, a biblically accurate representation of a query plan. But most importantly, a query plan is really something you think about very rarely in general, especially in terms of its performance and its optimizations. You think about it when you think about how can you optimize your queries, right? But the issue kind of we've been facing is that this bit that's really meant to be quite invisible has become really quite visible. And for the most part, we really wanted to optimize it so it's something that nobody really that uses the router has to worry about, and only we have to worry about. Like in a database, and I quite often compare a query plan to what an explain plan is in a database. It's the explain plan routes your query towards its shards, right? And a query plan routes its queries towards its subgraphs. And in a database, you never think about how long your explain plan takes. And you don't think about how long that explain plan, how much memory that explain plan consumes. But for us, it has been that. And we don't want that, and the plan has always been to really rewrite it. So let's talk about the existing query planner and why has it become something that's visible. And so a lot of this, and perhaps not a surprise to a lot of people, is because we run this inside a V8 process. All the planning happens via an external process. So here, if we go back to this diagram, and I'll bring it up a few times as well. This bit here is what does the translation between V8 and V8 being the JavaScript engine and the REST process being the router. And so this translation becomes complicated, and especially once the graph gets complicated and once the operation gets complicated, the more cost we pay for this translation between the two. You gotta serialize, you gotta deserialize. The bigger the schema, the more deserialization you do, and sometimes you have to do it twice. And that's really, really impacting just query planning performance. In fact, a little bit of foreshadowing. When we internally, Studio runs the router, and when we switched that over to use the REST query planner, we saw a huge drop in just query planning duration. And in case it's not obvious, this is when we made the switch. And we could see just how much we've been paying for that translation itself. Obviously, some of it is just improvements that Rust brings to the whole rewrite process, but a lot of it is also just the fact that you've got to serialize and deserialize between the two. Another issue with V8 is memory. And a lot of the times what ends up happening when you have this sidecar process and you have a shared memory you think about is that V8 and Rust fights kind of for the memory space you have. And there's a lot of contention that happens. And especially the more complicated a query plan becomes, the more memory you're going to allocate. And JavaScript kind of likes to consume a lot of memory, a lot more than it actually needs. And that's just how that language works, and that's fine. But what ends up happening whenever we have to reload the schema or reload the router or reload the config for the router, kind of that memory spike is quite large. Another thing here is that because of this kind of sidecar process, we're also unable to really figure out which parts are which quite easily. Of course, like if we put in the effort and the time, we can slot in and see, okay, this process was the one that had that memory spike, and this process is the one that dropped a lot of allocations, and this is the one that allocated a whole lot. But for the most part, it's really difficult to track and to measure this memory. The other thing is CPU. So we're talking a lot about resources. And the CPU usage is also what we see usually in our dashboards. And I was jet-lagged, and you just redesign Datadog when you're jet-lagged at 4 in the morning. So this is what we would usually see in our Datadog dashboards, is that these spikes pop up every so often as soon as we need to reload the schema, or we need to reload the config, or just the router needs to be restarted. And this happens because we need to drop the cache for various reasons. You know, schema reloaded, some of the operations are stale in the cache, and so we need to drop the cache. And as soon as we need to replan everything, we get a spike. And so you get a whole ton of these over time, and it's not really a good way for us to look at our CPU with these spikes. Another reason why V8 does not quite work for us in this case. But a lot of the times for us engineers maintaining this is that it's really difficult to debug without putting in the effort and the time into really getting to know V8 as a system. And we really want to be able to maintain a stable and reliable runtime, and this sort of stands in our way a little bit. And again, this becomes a lot more complicated as soon as an operation and a query plan is a lot more more complex. And to be fair to V8, all of these things are possible. You're able to zoom in and optimize, and we see a whole bunch of tools do it. Chrome does this. They run a V8 sidecar. But it requires time and effort to really, really zoom in and start optimizing the JavaScript runtime inside of your Rust process. And if you remember, we really want to stand by, and we know that our decision has been to write the router in Rust to be able to really scale and to be able to build a reliable runtime. So this rewrite process, we wanted to go from this to effectively this, where everything runs inside the router itself. So how did we go about the rewrite? Well, I think you can probably think of this as like, well, you have A and you want to get to B, so all you have to do is just copy over the entire implementation. But we wanted to go about it with specific goals in mind and kind of try to achieve those goals as we go. And you probably guessed the first one is to remove V8. But effectively, the other two was to really make sure that the system we have is debuggable and maintainable by us, and that we do this right. And if we do this right, kind of the first 2 points come a lot easier. And so I'll talk to you a little bit about how we went about getting this right. Correctness. So in terms of correctness, it's really, really simple, I think, on what we want to achieve. We basically don't want to have an effect on what the router currently does. That's it. It should be an invisible swap between the two implementations. Everything remains the same. We resolve operations just in exactly the same way as they have been done before. the same data gets returned back. So we went on to this rewrite process and wanted to figure out and make sure that the bugs we find that we find these bugs early on when we do the rewrite, or we keep consistency between the two. And one of the first things that really helped us make sure that we stay in line in terms of this goal of correctness is just using a formally verified type system. And that in its own prevents a whole lot of bugs. Again, a Rust engineer talking to you about Rust. Oh, no. I think in Paris, this is a side note, in Paris in 2018, when I went to RustFest, they made us sign a note where you have to talk about Rust whenever you get a chance to talk about Rust, and I think they call it the Paris Accords. And so using that really helped us find and maintain a reliable rewrite right from the get-go. And just by that, we were able to find bugs in our own rewrite implementation. In fact, at one point in time early on, we were running a bunch of tests, and there is one particular line in our code that does a vec with capacity, which allocates space based on the number of capacity you give it. And we got a kernel panic. And Rust basically said, you were trying to allocate 211 terabytes. I can't let you do that. Why did you think you could do that? Which basically spotted a bug in something very minute, which generated a bunch of options, and we were generating way too many options, which was a bug in our rewrite implementation. But it's nice that we got a little bit of a heads up from our handy formally typed system that you can't allocate 211 terabytes. Aside from that, we basically wanted to make sure we get identical plans. And that really comes down to differential testing. You probably expect this. Sure, you're implementing another version. Of course, you want to compare A to B. You want to make sure the two apples are exactly the same. And differential testing is something that is used quite often in compiler work. Along with invariant testing, it's how we make sure that an implementation is correct. And we use that usually in fuzzing and test case generation to be able to provide a particular input and just continuously compare it between the two implementations of a thing. And that input gets continuously generated, so you are able to get 211 terabytes of data, perhaps, to really test against a particular thing. But here, what we wanted to do is to kind of have a little bit of a loop. We wanted to create a plan. We wanted to create a planner, plan the operations in two different implementations, compare the two plans, find bugs, and keep going in a loop as long as no bugs are left. Pretty simple, and we were able to find a whole lot of them. And what we noticed really is that the first set of bugs we found were the things that really got lost in translation between the two layers, where certain algorithmic differences between JavaScript and Rust and certain implementations and the underlying libraries meant that some of the output was in a different order. So for example, we'd have things like this sort of, let's look at this plan, for example, where you have two parallel fetch nodes that could be like this in the JavaScript plan, but could be like that in the Rust plan, where from the execution point of view, these will return the exact same data. And we really don't want to be able to, we really want to be able to see the actual bugs rather than the array being a little bit out of order, because execution will remain the same. Sort of similarly, we'll have differences like this, where variables are sorted in a different order. And this, again, is semantically equivalent, because variable order doesn't matter. If this was directives, then this would be a different conversation, because the order matters there. But with variables, it doesn't so much. And so we needed to get rid of this noise and really be able to focus on the actual bugs in the implementations. For example, what if we're missing a node? That's going to be important. But so much of the noise being just ordering differences really didn't help us focus. So what we did is introduce a semantic equivalence function. And so what that did is help us determine when ordering things really didn't matter, then the two plans are semantically equivalent. And you kind of have to think about it as you implement it and really think about the specification and really think about GraphQL in general. Sometimes order will matter and sometimes order doesn't. And we keep kind of improving on this as we go through our testing, seeing the difference between the two. And so this circle kind of turned into this. We semantically compare different plans. So the one thing we did want to focus on is actual operations that everybody who uses the router uses, because those most certainly, definitely, absolutely have to be correct. So what we wanted to do is to be able to test it on actual operations. If you use the router and you use GraphOS and you use Studio, you send us a whole bunch of your metrics and your operation signatures. And those are used for all the features that you see when you use Studio. But we can use those operations also to do testing and to make sure that this implementation is correct. So in our entire corpus, we've got about 2.5 million unique operations that we can now semantically compare between the two implementations. And this, of course, found some bugs. And what was interesting about this set of bugs, while there were actually some cases, oh, yeah, that's an off by one error. Oh, that's also off by one error. But a lot of the times, we actually found bugs in the JavaScript implementation, which was interesting. And it really got us digging into the whole kind of query planner as a system itself. But given this corpus of 2.5 million operations, at this point, we're at this high of a match rate, 99.97% percentage of operations match. This is great. There's 410 that don't match if you're doing the math. And we're still optimizing those and looking into them as we speak. So this will get higher. But, so we're doing this locally on this corpus of operations that we have, but is that enough? What we wanted to do is a little bit more. And a lot of this comes from the fact that in our corpus of operations, not all graphs will send us operations. Like you will have a staging graph, or you will have a load testing graph that, for many reasons, probably doesn't need to be sending operations or operation signatures to GraphOS. And so what we wanted to do is to be able to shadow test in environments in a cold path of the router to compare the two results. And so we've wanted to kind of look into the cold path, hot path of testing here, and focusing specifically on the cold path and being able to perform this comparison without affecting router's performance and without affecting router's CPU consumption or memory consumption. And so we've done a whole bunch of load testing, and here's kind of the plan that came up that didn't affect the router in any particular way, any particular visible way. So the router spins up a whole bunch of threads when it operates. This is an underrepresentation of the number of threads it spins up. A whole bunch of them usually are the ones that are processing your query plans. What we wanted to do is to spin up an additional thread, and that one's very limited. It only has a queue of 10. This means that we're able to process very, very few operations, but given usual workloads, this will give us a large enough comparison or a good enough statistically accurate comparison between the query plans. This number also meant that this cold path execution doesn't affect the router, any routers running in any particular visible way. but gives us a large amount of operations to actually run comparisons on. And we've done similar things when we've launched Rust GraphQL validation, which was maybe 20% faster in Rust. We did this for API schema processing, which also used to be done in JavaScript, which is also maybe 15x faster. And we've done this for usage analytics processing, kind of running this in a shadow testing mode and making sure that what we have implemented is correct. And so the shadow testing got released in 1.5.3, which was at the end of August. And this let us look into the actual data from the actual workloads and how the two implementations compare. Along with that, we sent some metrics. So these metrics are hotel metrics, so you can see them when you build up your dashboards. But there are also metrics that we can see. So with the dashboards individually, again, a Datadog dashboard representation done at 4 o'clock in the morning. We can look at the comparison between the two for deployments of a router. This is our deployment of the router, and see what the mismatch and match ratio is between the two. And we can also look at the duration comparison between the two implementations as well. This is, for example, the one that was redesigned at 5 o'clock in the morning this time for our own deployment of the router. This whole shadow testing process, while being done on a small thread of a queue of 10, meaning so few operations get sampled, we were still able to process 95 million operations since August and really look at how our implementation compares in the wild. And this also found bugs. An asterisk here, while the font gets bigger, the number of bugs we find are actually a lot smaller as the time went by. I just wanted to keep myself entertained with these particular sets of slides. And a lot of the bugs we actually were able to track were performance related. But also, given the data, we were also able to track how well the query planner performs. And that's how we get the 10x, the number 10x. Really, it's the processing of those 95 million operations. Right. But what we wanted to look is the mismatch and match rate. Right now, those 95 million operations are looking a little bit lower than our local testing. It's at 99.6. And I think this number is good for public preview because most graphs, and there's about 300 of them, I think 270 of them get 100% match rate. There's a few that don't. This is good for the public preview, but that's not good enough for GA. And our hope is that for GA, we're able to get to this. And a lot of the mismatches we're looking at the moment are some of the semantically equivalent things that we didn't think about when we started writing the comparison function. And a whole lot more of them are actually paths that the Rust implementation chooses that are a lot more optimal than what the JavaScript implementation chooses, which is why I don't think we'll be able to get to 100% because I don't think we want to go backwards with the Rust implementation and kind of keep the optimizations in rather than have to take them out. So that's our plan for the mismatch rate for GA. But talking about GA, let's talk about what it is that we're going to get to in the future. So eventually, we want to get to the hot path and actually running the Rust query planner and not having a V8. What we wanted to do once we got this much confidence in our implementation is actually run our own instance of the router, the one that powers Studio, without V8. And here's the numbers that we got. Again, we saw a glimpse of this, I'm foreshadowing. A whole bunch of our query planning duration went down. And it got a lot flatter. We don't have these spikes anymore for really complex operations. We were also able to see a much, much flatter router CPU utilization. This is where the router got deployed, and kind of the graph after that is a lot more flat, and we don't get the spikes we saw previously. This is great. And also, we saw a pretty significant drop in memory utilization as well. And I think this is sort of representing all of the pods that are currently deployed. And sort of that drop was very, very obvious, a lot more obvious than the CPU utilization drop, although the spikes were pretty steep. But sort of all of this leads up to the fact that router 1.56 has the public preview of this Rust implementation. And really, we want you to try it. And really, in order for us to go to GA, we need your help to try it and tell us if you see anything that's missing or wrong. Here's how you enable it. There's a router config flag to start the Rust query planner, and to get rid of V8 and to really see the memory in the CPU drops, you'll also have to enable the new introspection mode. And all of this really gets us to a router that runs solely in the native implementation. Yes. All right, so what does GA look like? We have a directive we still have to implement, and that's being implemented right now. It's the context directive. We can't go GA without that. We really want to be able to get to that 99.9% and do a whole lot more testing. I think about it this way. I would rather have, if you're building a house and you're putting together foundation, I would rather spend more time in making sure that foundation is solid and lasts for many years to come, rather than having it and then 6 months down the line, everything goes to shit. I clearly have never built a house. And we also really want your feedback, because we don't want to go GA and then have it not work in the way that you're using the router. And so a lot of this, these are the 3 things we really need to get right. Our plan right now is by the end of the year providing good feedback, but if we need more work and this needs to be right, maybe a bit longer. You can read it on the docs. I've got 2 more things. 1, what's next? The engineering team is really, really excited to finally be on a path to really get rid of V8, because I think that really gives us the opportunity to optimize and to really build the runtime that we all wanted when we started on this journey 3 years ago. Query Planner was always meant to be in Rust. It just took us a bit longer, and we're really excited to finally get there and be able to really start to think about a scalable and reliable runtime in the way that we have never been able to see it before. And that's really the most exciting for us as the engineering team. I think the product team and the leadership team will probably have other things to say, but for us, that's like, the Rust engineers are happy they don't have to deal with the JavaScript runtime anymore. and really, I think it'll be really great for everybody else to be able to see that drop in memory and CPU and not have to worry about why there is something that spikes your CPU up to God knows what, 200 terabytes of memory being used, or gigabytes of memory. Anyways, I am on stage representing a whole bunch of people. This was an effort in alphabetical order by Chandrika, Derek, Ducky, myself, Jeremy, Jesse, Renee, Sachin, Simon, and Tyler. And huge effort by everybody involved. Thank you so much for staying a bit longer and listening. Appreciate it.